explained why, or I explained how this divisibility by 7 trick works. We were able to show that this crazy number right here is not divisible by 7. In fact, we showed that it has a remainder of 1 upon division by 7 by going through 3 steps, 3 relatively easy steps. The purpose of this video here is to explain why this stuff works. Kind of a harder question, but we'll see how it goes. So it all comes down to this little grid right here. So make sure we understand this grid first, then I'll go through and talk through how it relates to these steps. So this grid right here is just telling you the remainder upon a division by 7 of these 6 numbers. So 1 obviously has a remainder of 1 upon division by 7 because 0 7s and 1 more would get you to 1. 10 has a remainder of 3 because 1 7 and 3 more. 100, it turns out, has a remainder of 2 because 14 7 gives you 98. You need 2 more to get to 100. Maybe you know that, maybe you don't know that. I'm going to show you a way to figure out this too without ever knowing that you need 14 7s to get 98. And once we figure that out, we'll be able to find the rest of these numbers. So how this stuff works is, maybe I'll skip the 1 and the 3. I'll leave that as kind of self-evident that, yeah, for sure, for 10, the remainder would be 3 upon division by 7 because you'd need 3 more than 7 to get to 10. Fine. For 100, the idea is to not consider the remainder upon division by 7 of 100, which is weird. Instead, think about it as 100 is just 10 times 10. And 10, as we figured out here, has a remainder of 3. So 10 is some number of 7s, 1 in this case, but some number of 7s, plus 3 more. So instead of thinking about 100 as 10 times 10, we can think about it as 10 times this thing. The reason it's helpful to group them like this is because when we distribute this 10 through, we will get this. We will say that instead of 10 times 10 is 100, 10 times 7, 70, but you don't even need to know that's 70 with 30 left over. This 70 has to be divisible by 7 because it's just some number of 7s, 10 in this case, but some number of 7s with 30 left over. So I guess the point that I was getting at is if you want to know that the remainder upon division by 7 of 100 is 2, you can instead say that the remainder upon division by 7 of 30 is 2. 7 times 4 is 28, leaves 2 more. And where'd that 30 come from? It's this 3 right here times 10. Because the remaining 7 that makes up this 10 will definitely be divisible by 7. So it's just the 3 that I'm worried about. And so how do you figure out this 6 right here? All you got to do is take this remainder of 2. You got to say that 1,000 is 10 times 100. But 100 is just some number of 7s. I don't know how many. I do know how many. It's 14. But pretend you don't even know how many. Just put an X down or something. Plus 2. 100 had a remainder of 2. It was a bunch of 7s and a 2. So instead of doing 10 times 100, I do 10 times this expression. What I get is 10x of these 7s plus 20. 10x of the 7s, that's definitely divisible by 7. It's just whatever x was times 10 of the 7s. A bunch of 7s, it's divisible by 7. All I care about is this 20. You don't care whether 1,000 is the remainder upon division by 7 of 1,000. You care about the remainder upon division by 7 of 20. 7 times 2 is 14. It takes 6 more to get to 20. So the remainder here is 6. Just like the remainder here is 6. Same thing. And so how did I get this 4 right here? I didn't look at 10,000 at all. I said that 1,000 left me with the remainder of 6 and a bunch of 7s. Multiply that by 10. I still got a bunch of 7s, and now I got 60 left over that I got to deal with. Well, that 60, I guess 8 times 7 is 56. So that 60 is a bunch of 7s, 8 more, with 4 as a remainder. It's 56 plus 4 more get you to the 60. So that's this 4 right here. Similarly, to get to this 5, 4 times 10 is 40. 40 leaves a remainder of 5 upon division by 7. 7 times 5 is 35. Get you this 5. Like, all right, you're starting to rattle those off pretty quickly. Why don't you keep going? Because I don't need to keep going. Because if I cared about 1 million, the next number, the next column here, well, I just do 5 times 10 to get 50. And then 50 leaves a remainder of 1 upon division by 7 because 7 times 7 is 49. So my remainder here would be 1. But note my remainder here was 1. And since I figure out the next remainder just by looking at the previous remainder, the minute I see that there's a 1 here, I know that the number after that would be a 3, and after that would be a 2, and a 6, and a 4, and a 5. What I'm saying is this pattern right here is just going to repeat for over and over and over. This pattern is 6 digits long, and then it repeats, which explains why down here in step 1 I add blocks of 6, because this pattern takes 6 to repeat. I can't just add up this 9 and this 9 and say it's a remainder of 18, because it's not. This 9 right here constitutes 9 ones, but this 9 right here constitutes 9 threes. I can't add those together if I'm going to keep track of the remainders. However, this 8 right here in the 1 millionths place constitutes remainders of 1. So this 9 right here, each of these 9 count as 1, just like each of these 8 count as 1. Similarly, each of these 8 count as 1, and each of these 4 count as 1. These 4 numbers all count the same. They all count each as a remainder of 1. Similarly, maybe I need to switch colors. These 4 numbers right here all count the same. They all count as a remainder of 3. Because I know this is a remainder of 3 because it's in the tens place. This one, the 10 millions, I know that's a remainder of 3 because this pattern just repeats. And so on. So when I added this 9, this 8, and this 4, that's because this 9, this 8, and this 4 all count the same. Namely 1 in this case, but I don't even care what the number is, just that they count the same. 9, 8, 8, and 4. When I added up 9, 8, 8, and 4, I got 29. But I didn't care it was 29. Yeah, it's true it's 29 of these ones, but don't worry about it being 29 of these ones. Think about it as 4 groups of 7 with 1 left over. I can certainly group the 4 groups of 7 and not have a remainder. It's just the 1 remainder that I care about. Similarly here, I took the 9, the 6, the 7, and the 4 and added those up and got 26. But I don't care about that 26. Yeah, it's 26 of these 3s, but don't even worry about that. It's 26 of something. Well, I could take 21 of that something, and I could definitely make those into groups of 3, because 21 is divisible by 3. So instead of thinking about this as 26 3s, really it's just 5 3s, because the remaining 21 3s all divide evenly. All can be split up in groups of 7. So it's really only a 5 here that I'm concerned with as the remainder. Similarly, 1, 6, 5, and 5. And you're okay, you netted all those out. Why don't you just add up these numbers? Again, I can't add those up because this counts as 1s, this counts as 3s, this counts as 2s, 6s, 4s, and 5s. At this step, I could just do 1 times 1 plus 5 times 3 plus 1 times 2 plus 6 times 6 plus 4 times 5 plus 5 times 5. There's lots of divisibility by 7 algorithms that tell you to do that. I got a couple problems with that. You'd have to memorize this sequence, and you're doing quite a bit of math there. But if you get kind of clever, you can figure out, using these other steps, whether or not a number is divisible by 7 without doing all that math. And what it comes down to is back to this pattern up here. This pattern is actually nicer than it even looks like. You stare at this for a while, you see some numbers, but you don't see anything too pretty. But if you break it up kind of into this alternating idea, I got a 1, a 2, and a 4. It's a pretty nice little pattern, 1, 2, 4. But you're kind of skipping numbers there. But okay, maybe there's something. 1, 2, 4. What about the remaining numbers? 3, 6, 5. Ugh, doesn't look like anything too pretty. True, but instead of considering the positive remainder, we can consider the negative remainder. So what I'm saying is this 3 right here comes from the fact that if you had 7, you'd need 3 more to get 10. But you could also think about it is if you had 14, you would have 4 too many. So we could think about the remainder of 10 upon division by 7 as both 3 or negative 4. A different way to think about it. Similarly, this 6 right here, you could think about it as if you were taking 1,000 and dividing it up among 7 people evenly, you'd give a bunch of them away and you'd be left over with 6 that you couldn't evenly distribute. But if you had 1 more, then you could evenly distribute them. So you kind of have a remainder of negative 1 or a remainder of 6, however you want to think about it. Similarly, this is a negative 2. So I like this pattern with the 1, 2, 4 thing going on here. I didn't like the 3, 6, 5. That wasn't that pretty. So let's consider the negative remainder for those 3 numbers. What you'll note is that I end up with negative 1, negative 2, and negative 4, which is going to be really handy because up here I had 1, 2, and 4. That's where step 2 comes from. This idea of alternate subtracting blocks of 3 just comes from the fact that I got a positive 4 and a negative 4. I got a positive 1 and a negative 1. I got a positive 2 and a negative 2. If I could line those up, I could kind of net them out, which will end up being what subtracting is, to keep track of just how many 2's I have, how many of them go away with these negative 2's. So that's what I'm doing in my next step. So the way to think about this next step is this 5 right here really counts for 5 5's. You can think about this as a remainder of 25 coming from this 5 right here, the 500,000. Or you can think about it as 5 negative 2's. Instead of thinking about 500,000 as leaving you with the remainder of 25, you can think about 500,000 as leaving you with the remainder of negative 10. Think about each of these 5's are negative 2's. This 5 right here, you can think about that as 5 groups of remainders of 4. This 6, you can think about it as 6 groups of negative 1, 2, negative 4, and 1. Note that this negative 2 and this negative 2 line up pretty nicely. This 4 and this negative 4 line up pretty nicely. This negative 1 and this negative 1 line up pretty nicely. So if I write the first 3 digits on top of the next 3 digits, my negative 2 will be right on top of my 2, my 4 will be right on top of my negative 4, and my negative 1 will be right on top of my negative 1, right on top of my positive 1. So this 5 and this 1 right here, really I think of as 5 negative 2's and 1 positive 2. If you have 5 negative 2's and 1 positive 2, you have this, and you want to net them out, you'd be like, well, I got 5 of these things, 5 in the negative and 1 in the positive. I guess I'm left with just 4 in the negative. So this 4 right here really represents 4 negative 2's. Right, I had 5 negative 2's, and then I also had 1 positive 2. So in net, I have 4 negative 2's. This 4 right here represents 4 negative 2's. Similarly, when I subtracted these 5's, I said this 5 represents 5 groups of 4, whereas this 5 represents 5 groups of negative 4. So if I net those out, I end up with 0 groups of 4 or negative 4. That's where this 0 comes from right here. The reason you have to alternate the adding is because this 5, these were negatives and positives. Negatives, positives, negative, positive. But this one was positive and this one was negative. So that idea of the negative and the positive being switched, I had to account for by subtracting in different directions. By giving you the freedom to subtract in any direction you want by doing down, or up, down, up, I lose track of whether this represents 4 2's or 4 negative 2's, whether this represents 0 4's or 0 negative 4's, whether this represents 5 1's or 5 negative 1's. I just know that the number furthest left is going to represent the 2's, the number in the middle column-wise is going to represent the 4's, and the number on the far right column-wise is going to represent the 1's. And maybe they're negative, maybe they're positive, I don't know, but I do know that all 3 are the same sign. With those numbers, we can jump to step 3 and figure out, kind of net out all of our remainders. The reason you always start with the number that's by itself, whether it's by itself up here or by itself down here, is because that comes from the middle column. And the middle column always represents your 4's. So really this 0 right here should be 0 4's. So whatever number you have right here, you really want to multiply by 4. Whatever number you have right here, since they represent 2's, you want to multiply by 2. And whatever number you have from this column, since they represent 1's, you just multiply by 1, you don't do anything. So you're like, wait, I don't see any multiply by 4, double add, double add. Well, actually, double add is exactly multiply this guy by 4, this guy by 2, this guy by 1. Because we first double this guy, now it's been doubled once. Then we pick up this guy, now we have both of them and we double them. So now this one's been doubled once, this one's been doubled twice. And you add in this guy. This guy never got doubled, this got doubled once, this got doubled twice. I'm accounting for the fact that this represents 4's, or maybe negative 4's, this 2's or negative 2's, this 1's or negative 1's. And so what I'm doing is I'm keeping track of how many of the remainders I'd have from each of those. If those remainders make even groups of 7, then what that means is that this original number must have been divisible by 7. When I went through all this work, what I figured out, if you double add, we got 13 here. And then we say, well, 13, the remainder upon division by 7 is 6. And 6 is not divisible. It's not a remainder of 0. So that means that this number is not divisible by 7. That's a little bit strange because this number has a remainder of 1 upon division by 7. What this comes from is all three of these were negative because of the order I added them in. So really this should have been negative 13 right here. There should be a minus in front of this. There wasn't a minus because I didn't keep track of the negatives. I said it didn't matter because I don't care if you have negative 0 or positive 0, negative 7 or positive 7. Either way, if it's divisible, you got a multiple of 7. So we throw it out. It gives you a little bit more freedom, but you lose track of what the remainder was. This should have said negative 13, which would have made this remainder positive 1. But either way, it's not a multiple of 7, so this number is not divisible by 7. Finally, I guess that explains, maybe I shouldn't write the 13 or 6 here because that was down here. I guess that explains why this three-step algorithm works, or at least it tries to. What about Irv's method over here? How did that work? Well, what Irv did is instead of thinking about this 51 right here as 5 tens and 1 single, as 5 of these things that leave a remainder of 3 and 1 of these things that leave a remainder of 1, he thought about it as 51 of these things that leave a remainder of 1. Similarly, instead of thinking about 61 as 6 1,000s and 1 100, he thought about it as 61 100s. Instead of 500, how do I say this? 500,000, 550,000, he thought about it as 55 10,000s. I guess that makes sense. So what I'm saying is Irv saw this pattern, the 1, 2, and the 4, and he didn't want to mess with this 3, 6, 5 thing. So instead of saying you have numbers from both of these columns, he just said you have a whole lot of these. Instead of numbers from both of these columns, you got a whole lot of these. Instead of numbers from both of these columns, you got a whole lot of these. Only the 1s, the 2s, and 4s, which will be the key to this double add thing that we do in step 3. Just like these represented 1, 2s, and 4s. So really all Irv had to do was he looked at these 51s. He said, I got 51 things that leave me with the remainder of 1. I could just figure out the remainder of 51 upon division by 7. It's 2. Because 7 times 7 is 49. That leaves 2 left over. But why bother figuring out the remainder of a 2-digit number upon division by 7 when we have a fancy little trick for figuring out the remainder of a 2-digit number upon division by 7? Whatever's in the tens place counts as 3. And whatever's in the ones place counts as 1. This 3 right here essentially is this triple. The reason we said we took this 51 and said 5 times 3 is 15 plus 1 is 16, and then looked at the remainder of 16 and got this 2, was because we could take advantage of that fact. So you can either think about this as 5 tens and 1 single or 51 singles. Either way is fine. Same idea here. For this 61, well, let's see, 61, if I triple it, I have 18. If I triple the 6, I have 18, and add 1, I have 19. That leaves me with the remainder of 5. So 61 must have a remainder of 5. But then you got to remember that each of these 5s are one of these 2s. So each of these 5 account for a remainder of 2. So this really represents 10 right here, even though it says 5. And finally with this 6, yeah, 55 has a remainder of 6 upon division by 7, either because 7 times 7 is 49, and 49 needs 6 more to get to 55, or using this triple add method, 5 times 3 is 15 plus 5 more is 20, triple because of this 3 right here, and then just add because this is just 1. And 20 has a remainder of 6. Either method is fine, but either way you got to remember that these are 4s, these are 2s, and these are 1s. So you could just multiply this by 4, multiply this by 2, multiply this by 1, and add up those products. Or you could do the double add method, because that ensures that this gets multiplied by 2 twice, aka multiplied by 4. And this gets multiplied by 2 just a single time. Either way, you'll end up with this remainder of 1, which is the remainder of this number upon division by 7, which tells us that this number is not divisible by 7. The last point that I want to make is doing this method. I pointed out that we lost track of the sign. So when I got this 13, which I could think of as 6, that was not my remainder upon division by 7 of this number. Because really what this 6 represented was 6 negative 1s. And 6 negative ones would be negative 6, which is a remainder of 1. But I lost track of the fact of whether this was positive or negative. I never lost track of whether this was positive or negative because I only used this column, and this column where all three were positive. So that's why this method will always tell us the actual remainder, whereas this method will just tell us whether the remainder is 0 or not. All right, maybe that explains why all this stuff works. I'll stop this video here.